Maths lets me combine my career with my passion. As an oceanographer, I get to spend my life studying the waves.
Studying maths at the University of New South Wales leads to more career opportunities than any other qualification.
I chose maths at UNSW because I can work in any industry. Medicine, finance, computer graphics, meteorology, security intelligence. There's nowhere a maths graduate can't go.
The University of New South Wales School of Maths, #1 in Australia.
You do the math.
The School of Mathematics at the University of New South Wales is the largest of its kind in Australia. There are over 70 mathematicians working in its 3 departments, which are pure mathematics, applied mathematics and statistics. The school has an international reputation for being a leading research centre and developing new mathematical knowledge. It offers the widest choice of courses in Australia and the most flexible degree programs. Hi, I'm Clio and this is the School of Mathematics at the University of New South Wales. Let's go and have a look. Let's go and see Mike Banner. He's the professor who's just won the Sverdrup medal. I want to find out all about it. Now you won a medal for your work.
Yeah, I was very fortunate. I've been honoured to win the Sverdrup medal for air-sea interaction from the American Meteorological Society.
Do you have it here?
Yeah, sure.
Show us, show us.
There it is.
Wow, is it real gold?
It's real gold plate.
And what did you win it for?
Well, this is a prize in recognition of my work in air-sea interaction over the past 25 years, and it highlights my contributions, particularly in regard to wave-breaking effects in assisting and enhancing air-sea interaction.
And who uses your research? Does your research become crucial to certain people?
Well, indeed it does. I mean, there's global coverage of weather, there's global coverage of sea states, and all kinds of other products related to air-sea interaction that are vital for these global models that are available on the internet, and they're used by many agencies around the world, land agencies and ocean-related agencies, and all sorts of groups use this information.
A tour of the maths department wouldn't be complete without meeting Matthew England. He uses mathematics to work out how the oceans work. This is his office. The door's shut. Not looking good. Do you know what? I reckon I know where we can find him. There he is. Matthew.
Leo.
I knew you'd be
G'day.
down here. You think you're having a surf?
Well, I was, but it's pretty small, so I probably won't go out today.
So that means I can ask you a couple of questions?
Yeah, sure thing.
I wanted to find out, or if you could tell me a bit about CMAP.
So CMAP's the Centre for Environmental Modelling and Prediction. It's just part of the School of Maths. It's a centre that our research is about using mathematical models to look at the ocean and the atmosphere.
So you need mathematics to do that? Why not be part of some, I don't know, geography or marine biology area?
Yeah, we need maths because the system's basically governed by some quite long and complicated equations, and the physics is quite simple, but the mathematical techniques are relatively complicated. So we need good maths graduates to come into the field and find out about how the oceans work.
What area do you work in or do you specialise in?
So the main thing I look at is large-scale ocean currents and how they affect climate patterns.
Large scale as in worldwide?
Yeah, global climate patterns, but with an emphasis on the Australian system. There's a lot of ocean around Australia, and we've got to sort of work out how those ocean currents feed into the climate that we get.
And can you tell me anything about this particular water here?
This bit of ocean's very nice. There's tropical water that comes down by the East Australia Current, and it brings a nice warm and mild weather pattern to the Australian east coast, and it's a very nice bit of ocean to swim in year round because it's warm and tropical water. Only gradually loses its heat, but it's a nice piece of ocean.
So do you think you'll go for a swim anyway?
I'll jump in. Yeah, it's worth getting in and getting wet.
Okay, I'll let you go then.
All right, see ya.
Thanks. President-elect of the International Council for Industrial and Applied Mathematics. What kind of role does that council play in the mathematical community?
Well, its role is really to develop mathematics and its applications worldwide. I mean, both in the developed countries, the US and Europe countries are all part of it, but also we are very keen to broaden out into the underdeveloped countries. Right now we have a project to set up a meeting in Africa. I think myself that the mathematics of sustainable development
That's a
would be a
fantastic
really
idea.
good title.
Are there mathematicians there at the moment that work in that area?
Yes, there are. It's quite an active field there. In some sense, I think that's one of the best developed fields in Africa.
So that's really interesting. So part of your role is to look at mathematics on a global perspective.
Yes, mathematics and its applications. The applications, as you know, are extraordinarily wide. We cover every application of mathematics, from building of ships and ecology and electricity and communications and industry and everything.
Sounds fantastic. Thanks for that. This next guy's a real numbers man. He's always got some interesting stuff to show people.
Hi, Clio.
Mike, you're a man of numbers. Can you
might
tell
say
me a
so.
bit about that?
Oh my goodness. Well,
Just a little bit.
I work with partitions of a number into numbers of smaller numbers or squares or whatever, and you get some big numbers there.
What's a partition?
That's where you try and express a number as a sum of smaller numbers or other numbers or numbers of a special sort. For instance, you take a number like 100 and ask how many ways can you partition 100 into positive integers, and there's stacks of ways of doing it. Millions, many millions.
Okay, so if I said to you, Mike, how many ways can you partition up a number like 10,022?
Holy mackerel.
Could you tell me?
That's enormous. Well, I can, as it happens, because I happen to have a table of the numbers of partitions up to about 12,000 here, right here on my shelf, as it happens.
That's exciting.
Which were computed by a student of mine many years ago. And so if we wanted to know how many ways there were of partitioning, you said 10,021, I believe. 10,021 will be here somewhere. As said, he's scrabbling for the number. No, it's back a bit more.
10,000.
Yes, well, for instance, 10,021. Well, there's the number of ways of doing it.
I love your office.
Oh,
What's
yeah,
this?
Fantastic. Well, that's a rug I made many years ago.
You made it?
I made that about 24 years ago. Yep. It took me about a year or 2 years to make it, mind you. You see, at the end of '76, we discovered this particular pentagonal shape, 5 equal sides, you see. And it's got very specific angles, all multiples of 20 degrees. And I just thought, what happens if I put 6 of the 60-degree angles together at one point? And it just grew like that. And what's special about it is not only are all the little pentagons exactly the same size and shape, but it spreads out and covers the entire plane. You see, and it's got this rotational symmetry. If you rotate it by 20 degrees, it's exactly the same.
What about these things? I mean, I can see more tessellations.
Well, more tessellations. Well, based on the same tile, I had these pendants made. This one is the same tiling as the rug, and I actually wore this at the time.
Well, this has been a very interesting chat.
I'm glad you think so.
Thank you.
Oh, good. See you later, Clio.
So Mike Hirschhorn is a pure mathematician, as opposed to an applied mathematician. I asked Tony Dooley if he could explain the difference between the two.
In a sense, mathematics is a whole continuum, and there's a fairly artificial divide between pure and applied. But at one end of the spectrum, certainly, applied mathematicians are thinking just about one specific problem. It might be flow of air over an aircraft wing, or it might be eddy currents in the ocean, or it might be studying the motion of pollen particles in a glass of water. They're trying to solve that particular problem. A pure mathematician should take a step back from these many different problems and say, what's the common thing that's driving, common theory that's lying behind these things? What's the common mathematical concept that can be used to explain them all?
Tony then told me one of his PhD students who studied the Brownian motion of stock prices now works in a bank and makes lots of money. I asked if he could show me how to do that.
Okay, let's find a blackboard and see what we can do.
That sounds good.
Let's get warmed up. We start with a whole bunch of particles which we put at the origin. If it's positive at the end of 3 months, you've won. If it's negative, you've lost. If it's 0, well, you've broken even. With a barrier option, these guys draw a barrier there, and if it's...
Oh, here's our expert witness, Dr Peter Cooke. Let's go and ask him some questions. Hi Peter,
Hi, Peter.
how's it going?
Good, how are you going?
Hey, can I ask you some questions about your work?
Sure, yeah.
Shall we go into your office?
Yeah.
Your career seems so diverse.
Well, I've done work on lots of different things, including poker machines, horse doping. I've been out to Long Bay Jail. I've been an expert witness and written affidavits for courts. I've recently done work on water usage. I've done many of those reports. And finally, my television career, which seems to have stalled, but I did an ad a few years ago for State Bank. I don't any longer have a copy of the commercial, but this was a poster that State Bank put in their branches.
I remember this one.
This was an ad for State One account, so...
And so is that your handwriting right there?
That's my very own handwriting.
I like your X's. Your X's are good.
Thank you.
Well, I'm interested in a whole range of things. I'm an optimizer. I find the best way to do things subject to constraints.
Rob Womersley is an applied mathematician who regularly consults for industry. For his research, he uses some of the most powerful computers on Earth.
I'm lucky to be at a university where there is a lot of infrastructure. It's a large university, research-oriented. But that's not enough. We have to have collaborative ventures with other universities in the state government, and even nationally to be able to have a hope of competing with overseas institutions. And that's where we need the really powerful computers, both in terms of speed and memory, to be able to handle these large problems.
And do you use that huge computer to work out, for example, how to distribute these points evenly on the sphere?
That would be one example. It seems like a trivial thing, but it's actually got lots of applications. An interesting one is that we hope to use that in what's called inverse scattering, which is if you get the scattered sound wave from an object, how do you then recover the shape of that object? And you can think of immediate military applications of that sort of thing with radar. How do you detect the shape of the submarine? What does it really look like? And that's a very intensive computing exercise, as well as using sophisticated mathematics.
Do you have any pictures here that you can show me about?
Well, this is the one here which shows you a little movie of the points rotating around the sphere, the areas and the coloration, which is significant, as well as the shapes. Some of them are pentagons, some of them are hexagons, and the weights have particular meaning in when we're trying to do integration over the sphere.
So wouldn't the areas have to be equal for them to be distributed evenly?
That's one of the things that we're trying to do. We would like them to be as close as equal as possible. However, there are some results that say you can't do it perfectly on the sphere. You can on the circle, but not on the sphere.
Isn't that interesting? Professor, tell me, is pure mathematics a waste of time?
Well, the answer is yes and no. Yes, in the sense that it's useless in today's terms. No, in the sense that it might not be useless tomorrow or the day after. Let me give you an example.
Please do.
So let's talk about prime numbers. Everybody, I think, at high school comes across prime numbers, and everybody thinks that they're completely useless. However, prime numbers are used in the encrypting systems that mean that information sent along telephone lines, in particular between hole-in-the-wall machines and the banks that are running them, can be sent in a way that's secure and cannot be mistreated or abused by other people. And so what was considered to be useless for hundreds of years turns out to be underlying really the whole economy that we live and walk around in.
So Moninya, why would a mathematician go to Antarctica?
Well, basically, everything that happens in the ocean can be described by mathematics. You can use mathematical equations to describe fluid dynamics, which includes ocean circulation. And so I went down there to collect data on what's happening in the ocean, and we can use that data then back in our laboratories to examine ocean circulation.
How did you collect that data?
What I was doing, I was actually measuring the temperature in the upper layers of the ocean. We were measuring the temperature down to a kilometre depth. The ocean's about 4 kilometres deep on average, and I was measuring the temperature in the top 1 kilometre. and we went on a transect south of Hobart all the way down to the Antarctic continent. I really wanted to go to Antarctica. It was the most awesome experience, and these opportunities are available to you as a mathematician, as an oceanographer. You get the most incredible opportunities because you're studying the ocean, and the oceans are all around the planet.
And so do you travel much apart from Antarctica? Have you travelled much?
I've been really lucky. I study coastal circulation, and so I've spent quite a lot of time up on the Great Barrier Reef studying the circulation around a particular island, Lady Elliot Island.
So again, gathering data.
Yeah.
And then you come back here and you might then do the mathematics once you've got the data.
We'll spend a week in the field collecting data, say at that island, and then spend the next 6 weeks looking at the data and analysing it and comparing it to previous times as well.
We're going to see Diana Combe. She has this really interesting take on the family tree. I've heard you speak about the Maths Genealogy project. Is that how you say it?
Well, that's how I say it, yes.
And so, can you tell us a bit about it?
Oh, well, it's a project I bumped into on the web in the United States for tracing people's mathematical family history. So, from my point of view, it traces me back to my PhD supervisor, him to his supervisor, and so on. I think this is interesting because I've always been interested in the development of mathematical ideas, particularly over the last 300 or 400 years, and the way the ideas of calculus and algebra have changed, and to be able to sort of trace myself back in a sense to the big mathematicians at that time has been really interesting for me.
And who do you go back to?
Oh, I go back to all the famous people in Germany, like the Euler and the Bernoullis and Lagrange and Poisson in France. Yes. Would you like to see my family tree, Clio?
I'd love to.
Well, this genealogy project sells you t-shirts with your family tree. So I have a t-shirt with my family tree, which takes, here's me, I did my PhD a couple of years ago at the University of Sydney, to my supervisor, and where and when he did his PhD, and so on. It traces back through the United States, and finally to France, and then to Poisson in France in the early 19th century, I think, and to Lagrange. So although my research is in areas of algebra and patterns of symmetry, I seem to trace myself right back to the mathematicians at the time of the start of calculus.
Now, one of the most famous family trees in mathematics is based on Paul Erdos, one of this century's most acclaimed mathematicians. If you've ever published an article with Erdos, you're nicknamed Erdos number 1. If you've published an article with someone else who's published with him, then you're nicknamed Erdos number 2, and on this goes. Well, as it happens, we have an Erdos number 1 here at the University of New South Wales. His name is George Szekeres, he's 91 years old, and he still comes to work almost every day. I caught up with him while Mark Hirschhorn was there. Do you enjoy still coming to work every day?
Enjoy?
Yes.
It's hard work, but I do. Do we enjoy that?
I think you enjoy it. You come in 4 days a week, don't you?
It's not a matter of enjoyment. Well, I'm interested in a problem and I do it. So I don't know, enjoying is a bit misused word. Because what do you mean enjoying? When you go to a concert, you enjoy it. But I'm interested in a problem and do it, and try to do it.
So you're interested and it involves hard work, so you just have to do the hard work.
Hard work, well, the hard work is never really enjoyable. Well, after, when you have done it, then you might find it enjoyable. To have an Ardus number 1, at least I think 500 people in the world exist with Ardus number 1, but I am the very first one to have Ardus number 1.
I did not know that, really?
I am that old, you know.
Helen, I want to ask you some questions. Do you have time?
Yeah, sure.
You've just been to the library. Yes, picked up some more tomes. Is that for your PhD thesis?
Yeah, yeah.
Yes. Now, you left university for quite some time and then you came back to do your PhD. What were you doing in all that time away?
Yeah, I graduated in '92 with an honours degree in pure mathematics. I then worked for the Boston Consulting Group, a strategic management consultancy, all over the world and in a wide range of industries, from sort of coal mining, public sector through to telecommunications. I left them to work, first of all, for a legal publisher. I was only with them for a short while before I became the head publisher at Gordon and Breach Australian unit, and then later on looking after the whole of Southeast Asia and then marketing. Finally, about 4 years after I'd had enough of that, I worked as a telecommunications analyst for a stockbroker, London stockbroker.
Wow, so you've had quite a diverse career, and that was from a pure mathematics degree?
Yeah, what people don't realise about pure maths is, unlike other degrees which teach you what to think, maths teaches you how to think. Not what to learn, but how to learn. And that's a very attractive sort of asset to have. It means that you can move between industries, and when you're working for a different employer, you can work on a range of different jobs in a range of different sort of areas without being constrained to one particular framework.
And now you've come back to learn some more of how to think.
Yeah, basically how to think.
Are you enjoying it?
I love it, it's great.
So that's mathematics at UNSW. I've actually got to go and work now. I'm off to give a lecture.